Okay, so last time we were talking about power series and kind of finding different algebraic tricks to write different functions as power series. Essentially, we tried to take a given function, find a way to manipulate it to make it look like the sum of a geometric series, and then once we had it written as a sum of a geometric series, then translate that to an actual power series, and then we could talk about convergence and divergence and things like that. And we said there is kind of a reason behind all of this, and today we're going to kind of do that. The one thing I did want to point out, I don't really like the way your book does these last two sections, meaning I actually prefer to kind of flip the order around and do the last section and then the second to last section. But ultimately, they're essentially the same idea and the same topic. So we're going to combine the two, and I'm going to kind of do a couple of these videos today and a couple more tomorrow to kind of flesh out this idea, which is really, really important. And we finished last time, I think we had the function f of x equals e to the x, and we didn't actually have a way to generate a series for that, but I actually gave a series, and I said that with the series that I wrote out, it turned out that the derivative of that series was the same series, and since the only function we know that is its own derivative is the exponential function, then that would seem to imply that that series that we had was the series representation of e to the x. And today we're actually going to kind of prove that in a different way. And I will say this is somewhat cumbersome algebraically to write out. That's why I like the rooms with the big long whiteboard so I can write all of it out. So just kind of go along with it, and I'll try to get as much of it on here as I possibly can before I start erasing. But the idea is, suppose we have the function f of x equals e to the x. So right there, and we'll just draw the graph of the exponential like that. And we know that's the point 0, 1. And essentially what we can say is there a way to come up with a polynomial that will approximate that? Well, one thing I can do is I can start with the easiest polynomial possible, a constant function. So suppose I'm just going to try to generate a function here. Since I'm already using f of x there, I'm going to call the function that I'm creating p of x. And actually I'll call it p sub 0 of x. We'll see why later. Then I know if I have a constant, we'll just call it a sub 0, I can find a constant to approximate that. And clearly a constant function is not going to approximate that well at all, but it's at least a place to start. And we know that if we ultimately want to somehow get a series out of this, I need to have a center. Since I know the point 0, 1, I'm going to let x equals 0 be my center. So then what constant function works best? Y equals 1. Which of course makes a sub 0, 1, and it makes p sub 0 of x equal to the constant function 1. And that works as an approximation right at 0, but everywhere else it's completely wrong. So we want to make it better. And how do I make it better? Well, maybe instead of having a horizontal line, a constant function, maybe if I took a line with some non-zero slope, I could approximate it better. And again, the approximation won't be great, but it'll be better than a horizontal line. So now I need another function. I'll call it p sub 1 of x. And let's see, for a linear function, we'll just call it a sub 0 plus a sub 1 of x. And we already know if this approximation is going to be good, then I already know what a sub 0 has to be 1. So I can actually replace this with 1. Now I just need to somehow find a value for a sub 1 to make the approximation work. But if I want to create a line that approximates that function right there, right near 0, then the curvature of the line is actually important, the slope of the line, which means maybe I can make their derivatives the same. And if their derivatives are the same, then their rates of change are the same, and the approximation will be good right around 0. So take the derivative of both of them. For f of x, f prime of x is just e to the x again. And since I care about the value of the function right around 0, I know that f prime of 0 equals e to the 0, which is 1. Now take the derivative of this. So I get p sub 1 prime of x, derivative of the constant goes away, that's just a sub 1. But now I want the derivative to agree at this point right here at 0. So let's see. At f prime of 0, I want 1. So 1 has to equal a sub 1. And now I have my linear function. P sub 1 of x is equal to 1 plus 1x, which is just x. And now I have a line that will approximate, and this is where the picture starts to get messy. I have a line with a slope of 1 that will approximate the exponential right around 0. But clearly, quickly, the exponential will be really far away from the line. So what do I do to make it better? I get the curvature better. And how do I get the curvature better? Well, I care about concavity and things like that. Instead of using a line, I use a quadratic. Because, and I'm running out of colors for my markers here. But you think, if I drew a quadratic on this, I'll just draw it with dots, like this. Well, then the quadratic, because of its curvature, it doesn't work really well over here. But it works better over here. So maybe I can create a quadratic. So I'll call that p sub 2 of x, which is going to be a sub 0 plus a sub 1 of x plus a sub 2 of x squared. Again, I already know the values of a sub 1 and a sub 0, so I can plug those in. That's 1, and that's just going to be 1 plus x plus a sub 2x squared. I need a sub 2. Clearly, if I want these things to agree, they have to agree with their derivatives. And in this case, take the second derivative. So let's see. The second derivative over here of e to the x is still going to be e to the x. Over here, if I take the second derivative, let's see, p sub 2 prime of x, that goes away, that becomes 1. Bring down the 2, that's 2a sub 2x. Then take the second derivative, p sub 2 double prime of x, that goes away, this becomes 2a sub 2. And now, because I want this to agree with this at 0, I'm not going to be right, but clearly at 0, this is still going to be 1. I get 1 has to equal 2a sub 2, which tells me that a sub 2 is equal to a half. And now I have a second degree function, polynomial, to approximate the exponential. 1 plus x squared over 2. But again, ultimately, if we look at the dotted line, ultimately, this polynomial won't approximate that very well for very long. It doesn't approximate it well over here, and clearly the exponential will shoot up really quickly eventually. So how do I make my approximation better? Well, I have this 0, 1, 2. Go to the third degree, a cubic. And here's where I'm not going to write the whole thing out, but we should be able to see the pattern. P sub 3 of x will be a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed. I already have values for the first three a's. So p sub 3 of x is 1 plus x squared over 2 plus a sub 3x3. How am I going to find that? Well, since it's the third polynomial p, I'm going to use the third derivative. Over here, these will keep being the same. It'll always be e to the x, and at 0 we'll always get 1. So to save time, we'll just work over here. And we'll get p sub 3, the third derivative. I'm going to trust all of you can do these derivatives quickly in your head. That's a constant, so with the first derivative it goes away. That's a linear function, with the second derivative it goes away. That's a quadratic, with the third derivative it goes away. This is the only one that'll be left over. You'll have an a sub 3. First you'll bring down the 3, then you'll bring down the 2, then you'll bring down the 1, which is just doesn't matter. And we get p sub 3 triple prime of x is equal to 6a sub 3. I wanted to agree with this, which will be 1. And I get 1 equals 6a sub 3. So a sub 3 equals 1/6. And now over here, I can just erase this. And we'll get x cubed over 6 for my third term. And again, this will approximate it well, a little bit close, right around there. But ultimately, whatever cubic I draw will not fit it perfectly. So how do I make it better? I go with the fourth polynomial and the fifth polynomial. We've talked about error in approximations before. But we want to be able to see a pattern here, and there actually is a pattern. That's a 6, which just looking at this right here is 3 factorial, which is the power there. That's a 2, which when we took our two derivatives was really 2 times 1. That's 2 factorial. The coefficient there is 1, which is 1 factorial. The coefficient there is also 1 because it's constant, but it's really 0 factorial. And now if I see the pattern, I don't necessarily need to write it out. I can just expand. It'll be x to the 4th over, well, let's see, 3 factorial, so this will be 4 factorial, which is 24. X to the 5th over 5 factorial, which would be 120, and so on. And now we've kind of found another way to generate a polynomial to approximate a function. The one trick is, if you recall from the last video, this will actually generate the series that will generate e sub x. That's where we finished the last video. Right now we only have a polynomial. And kind of the trick of it, and the really complex math that we'll have to go over in the next video, because this one's already too long, is the thing that allows us to go back and forth from this polynomial that approximates the function to that series we created last time, which apparently is the function. We understand if this is an approximation, there's error involved. All this stuff over here, all these dots. And then the trick of it mathematically is to figure out what that error is, which at this point we've done repeatedly. But that's kind of a really important math thing that we'll look at. But for right now, the idea is I can take a function, I can pick a point, and then I can kind of generate these polynomials to approximate the function. I make the polynomials agree at a given point. Then I make them agree at that point for the first derivative, and the second derivative, and the third derivative. And then I kind of generate a polynomial term by term, degree by degree. There's a really important theorem that comes out of that we'll look at in the next video, which will allow us to generate approximations, these approximating polynomials, for any function that we want. But again, that takes more algebra like this, so I'm going to save that for the next video.